So now we will discuss Noether's theorem, which Noether's theorem answers the question that what happens when there is a continuous symmetry. Okay. So first we will state the result of Noether, and then we will try to we'll try to derive the theorem, Noether's theorem. Okay, but before I go to this discussion of Noether's theorem, I must mention that Noether, all of you must study this life of Noether, maybe from Wikipedia or something. She was a woman mathematician who collaborated and worked with many people, many stalwarts of the field, like Einstein, Hilbert. And the reason I'm mentioning is that she was an extraordinary mathematician, but at the same time she faced a lot of difficulty for being a woman. And that many of the people, many of us, when we study Noether's theorem, we are not exposed to the struggle of this courageous lady. So that's why I will suggest you to check the Wikipedia page and at least read about her life, because it's a story of extraordinary courage. And also, if you are interested more, at some point there was a conference at ICTS. I think it was in 2017, which celebrated Noether's work. This was a 2-day workshop. And then various aspects of Noether's work was exposed to a level where many of us can understand. So I strongly encourage you to also check this workshop and try to know about Noether's work. Okay, so with that, let me move to Noether's theorem, or it's often called Noether's first theorem. So Noether's first theorem says that whenever there is a continuous symmetry, of the Lagrangian, there is a conserved quantity which is preserved along the equation of motion. And vice versa. So it's a both-way statement. It says that whenever there is a continuous symmetry of the Lagrangian, there is a conserved quantity which is preserved. So conserved quantity means that which is preserved along the equation of motion. So let me remove it, because I said the same thing twice. And vice versa. It also says that if there is a conserved quantity, then there is a symmetry of the Lagrangian. So that's also very important, that Noether's theorem is a both-way statement. So let's first discuss the cases. Let's first discuss this statement more precisely in classical mechanics. So in classical mechanics, let's say there is a action which is time integral of a Lagrangian. Then it says that if there is a continuous symmetry, if there is a continuous symmetry, then there exists a quantity q such that ddt of q is 0. And vice versa. If there is exists a quantity q which such that its derivative is 0, time derivative is 0, it's constant along the equation of motion, then the Lagrangian has a symmetry. Okay, so let's first go to a simple example first before we go to the more elaborate discussions. So if I go to a simple discussion example, let's say I have a Lagrangian which is of this form. Sorry, phi star dot phi dot minus v of phi star phi, where phi is a complex number which depends on time. Okay, now you can clearly see that from this form of the Lagrangian, if I take phi goes to phi times a phase, then it leaves the Lagrangian invariant. Okay, and now before we go into more formal proofs, so let's first derive the equation of motion. The equation of motion. The equation of motion is simply that phi star double dot is equal to v prime of phi star phi times phi star. Okay, where by v prime phi star phi, this I mean is that derivative of with respect to phi star phi v of phi star phi. Okay, so this is the equation of motion, and of course it's if you take a complex conjugate of this quantity, that's also equation of motion. But interesting thing is that we can define a quantity q which is like phi star times phi dot minus phi star dot phi. Okay, you must be thinking that why I cook up this quantity and all this thing. We will go through, we will explicitly give derivation that how to give this quantity, but let's consider this quantity. And when you have this quantity, then you can check that ddt of q is, so ddt of q has one quantity which is phi star dot phi dot plus phi star phi double dot minus phi star dot phi dot minus phi star double dot phi dot. Okay, now these quantities, these two just cancel by just because they are same. For other two quantity, I use equation of motion. Okay, so I use equation of motion. So if I use equation of motion for other two quantities, I get v prime phi star phi times phi star phi minus phi star phi equal to 0. See, you see that the time derivative of this quantity is 0, so this is a conserved quantity. And this is this is an example of Noether's theorem, where you saw that your system had a continuous symmetry. So your system had a continuous symmetry. Why it is a continuous symmetry? Because theta can take any value. Theta can take any value from 0 to 2 pi. Okay. So if you do that, then you can see that there is we found a conserved quantity which is preserved along by because of the equation of motion. Okay. So let's now try to give a derivation of Noether's theorem, and then we will also generalize it to the case of fields. Okay. Very good. So let's say there exists a continuous symmetry. Let's say there is a continuous symmetry such that every field phi goes to phi prime, which is same as phi plus delta, let me call it delta hat phi, just to make it different from any arbitrary variation. Okay, so delta hat phi means this is a very particular type of variation, not arbitrary variation. Okay, such that the Lagrangian is invariant up to a total derivative. Okay, so in order to write these things, let's first write this delta phi in a more precise way. Let's say there is a epsilon a delta phi a, this, where this is a continuous parameter. And this is a small variation also. Okay, so in the case of this complex fields, you know, phi goes to phi prime, which is simply, very roughly speaking, is 1 plus I theta phi. Okay, I have taken this expression and I expanded it for small theta. Okay, then in this language, this is my epsilon, because this can vary continuously. This is my continuous parameter. And delta hat a of phi is simply I of phi. Okay. Now if this is the case, and let's say the Lagrangian goes to Lagrangian plus epsilon a ddt of Ka. Okay, so note that this Ka index has nothing to do with the space-time index. It is the symmetry, the number. So A captures number of independent parameter for the symmetry. If this is the case, then basically the action just goes to action plus ddt of epsilon a plus dt epsilon a ddt of Ka. Now again, if I choose this term, if I can set this term equal to 0 by boundary condition, then this transformation, then the transformation in 1, then the transformation in equation 1 is a symmetry. Okay, but you again see that in case of boundary condition, this is again subjected to the boundary condition. Okay, now let's now try to derive that what happens if this is a if something is a symmetry. So if the action is invariant, then what happens? Okay, but here I want to stress one important point. Then when you are trying to check the variation of the action, that how this action is changing and everything, so up to this stage, do not use equation of motion. So in order to check whether something is a symmetry or not, whether the Lagrangian is invariant or not, you should never use equation of motion. Because if you use equation of motion, then you will get a wrong answer. Why you will get a wrong answer? Because you know that when you put equation of motion is the extrema of the action, which means that any variation around the equation of motion leaves the action invariant, right? That's by definition, that the first order derivative of the action around the equation of motion is 0. That's how we derive equation of motion. Which means that if we use equation of motion, any small transformation, will look like a symmetry. Okay. So in order to check whether something is a symmetry or not, whether the Lagrangian is invariant after a total derivative or not, you should never use a symmetry. You should never use equation of motion. But then the next stage, when we ask this question, then we will see that the story changes. Now consider the case when the configuration satisfies equation of motion. Okay, so then what happens? So if the configuration satisfies equation of motion, then what we can do is that in the symmetry transformation parameter, what we wrote here, we can promote the parameter to a local parameter. Because you know that around equation of motion, any transformation, even the space-time dependent transformation, is also invariant, because any derivative around that point vanishes. Okay, if that's the case, then let's try to derive the variation of the action. Okay. So I have given, I will give the derivation in details in the note, but so in the LaTeX note you will see the derivation in details. And the bottom line is that you can show that the variation of the action simply takes this following form. Plus epsilon a dot So there is a epsilon A here plus epsilon A dot delta L delta phi dot plus dA phi. Yes, here. Okay. Now, if we try to compare, if epsilon A is time independent, then the last term drops out. And then the variation of the action, we already know that the variation of the action is something like of this form. Which means that in that case then this part is simply same as ddt of Ka, right? So just by checking that what happens when epsilon A equals to constant, we get that this whole term in the bracket, this bracket, first bracket is ddt of Ka. So let's put that. So then we get this is equal to epsilon A t ddt of Ka. Okay, and now for this term we again use integration by parts. So for this time, if we integrate by parts, what we get is that we get this minus del L del phi dot dA phi plus epsilon A del L del phi dot dA phi partial m. Okay. So this quantity has to be set to 0 by boundary condition. And then you see now this thing, this part here. Now consider that the configuration satisfies equation of motion. So if the configuration satisfies equation of motion, then any variation around the equation of motion is 0. So if any variation around equation of motion is 0, that means this quantity has to be 0. But if this quantity has to be 0, epsilon A is completely arbitrary. So if epsilon A is completely arbitrary, then we arrive at the expression that ddt of K of A minus del L del phi dot. Okay, so I forgot to put hat here. So this should have been hat. Yeah, this is also hat. So this is the Noether's conservation. So this is Noether's theorem in classical mechanics, and this quantity is the charge Qa. How many charges we get? So it is the number of independent parameters. Number of independent parameters of the continuous symmetry. So let's say how many independent charges do you? Okay, so let's discuss the point again. So we discussed in classical mechanics that if your Lagrangian has a symmetry, then the symmetry implies that there is a conserved quantity. But in order to check whether something is a symmetry or not, you should never use equation of motion. So in order to check whether something is a symmetry or not, you should never use equation of motion. But once you know something is a equation of something is a symmetry of your Lagrangian, then you can use equation of motion to come up with a conservation law, which is also known as the Noether conservation statement or Noether's first theorem, and that takes this following form. Okay, so this is the statement for classical mechanics, and this statement can be okay. I forgot to stress also. The Noether conservation law is also subjected to the boundary condition that this term has to vanish. If this term do not, so Noether's conservation law is subjected to boundary condition. So subjected to boundary condition. Okay. So all these things actually can be generalized to also field theory, and we will see how this can be generalized to field theory. And so in that case we will just have more indices, but the basic idea remains the same.